Yeah. So does it actually have any connection to Tesla? And Tesla's work?
Yeah, it's going to go into that. It's the Tesla car, right? It must have something to do with Tesla.
Oh, I thought maybe you just took the name and said, "Oh, now we're famous."
That's what I thought.
No, this. Yes, we can begin. You're here for the Tesla Engine Builders Association workshop. I'm from the Tesla Engine Builders Association. The nonprofit was incorporated in 1993. I was actually here at the first fair back in 1990 promoting the same technology. Long before Tesla Automobile or Tesla Motors was around, we were promoting the Tesla's concept should be used. And vehicles is one of the prime applications that he wanted to use for his device. And what Tesla Motors has done for us is they've given us half of the system. Tesla had a grand plan of having an automobile which was not just electrically driven, it was a hybrid. Tesla Motors has taken the philosophy that they don't want to incorporate so-called dirty engine in their devices. So they've chosen to go all electric, which raises a lot of other problems. The biggest complaint that Tesla owners have about their cars is the range. And they're trying to solve that problem with charging stations and trying to get around that basic problem that the car has. Whereas with a hybrid, like the Chevy Bolt, you can have unlimited mileage. You run out of battery power, you switch on the engine, and you continue to go. You can even charge the batteries as you go. So it has a lot of advantages being in the hybrid mode. But the biggest problem of the hybrid is what?
Also dirty fuel.
It's a dirty engine, right? So I would be against the hybrid too, just like Tesla Motors' philosophy, if it wasn't for the fact that Tesla came up with a whole new motor and a whole new engine, combustion engine, that would burn completely clean, run any fuel. Half of its fuel would be water. Okay, so it has the highest efficiency of any power plant in a small package, which means that you can put this power plant right in your car, just like other hybrids do. But it's going to be very efficient. You're not going to be getting your power from coal or nuclear or any of the other dirty sources that we're using, because it's great to say, okay, it's an electric car, there's no tailpipe emissions, but what's the total fuel cycle? Where is that power coming from? Okay, so it's like having blinders on if all you concentrate on is the tailpipe emissions, because we have smokestack power generation emissions or nuclear, horrible demon entities that are powering these cars. And the Tesla concept is to put the power right on board and put it where it's going to be efficient and clean. And that way we get rid of all this use. Tesla Motors' plan is, well, okay, we're going to all go wind, we're going to all go solar. But that just isn't going to happen. And then what's not mentioned is that these solar devices take huge amounts of energy to produce in the first place. So when you have a solar panel, are you really off the grid? You're independent from the grid, but you haven't divorced yourself from the grid because it still has all that embedded grid in it. It's grid city, okay? So when you recharge your Tesla from your solar panel, it's just a transitional way of providing grid power independently when you want it, and you can put the panels up and have independence from the sun, but it's going to take a lot of sun to overcome the energy that's embedded in those panels. And that's why you don't see solar just everywhere, because the economics of it just isn't there to make it practical. because it has all that embedded grit in it that you got to pay for. Okay, so a better vision, as far as the environment is concerned, is to embrace the engine. But all Tesla knew is all these piston engines, these diesel engines. Diesels are terrible as a piston engine. But when you burn diesel in a Tesla or conventional piston engine using diesel, it's very dirty, isn't it? Anybody knows that that's been behind a diesel. But if you burn diesel fuel in a Tesla engine, it burns completely clean. Much like your gas or oil burner in your basement for your oil furnace. Anybody have an oil furnace? Big oil tank in the basement? That's diesel, right? And when I grew up as a kid, everybody was burning diesel in the whole block, and there was no pollution. Why is that? Because they were using a jet and putting a jet of fuel into a burner, ceramic burner, at high pressure, and burning the fuel, what's the word?
Efficient.
Completely. That's where we run into problems with these piston engines. They do not have enough dwell time. It's a bang, bang, bang thing, and you don't have enough time to completely burn the fuel down to its non-polluting carbon dioxide essence, right? Because that's all we want out of the engine is carbon dioxide. But you're going to have a lot less, if you're worried about carbon dioxide, you're going to have a lot less carbon dioxide with the engine on the vehicle than to have the generator in the power plant. And one of the problems with having power transmitted or transformed in any form is every time you transform an energy from one fashion to another, say like from heat to shaft power or shaft power to electric on the line, you have huge inefficiencies. Okay? They are expressed in a logarithmic or exponential fashion, which means they don't simply add one inefficiency on the other. They multiply at a square. Okay? So by the time you get your power from the power plant, you might actually only be getting 15% or less of the heat energy that was used to produce that power in the first place. So it's almost a major loss. Most of it's wasted. Okay? Well, how can you solve that problem? Don't have conversions, right? Don't have transmissions. Where do you put the engine? Where do you put the converter? Where do you put that thermal converter? That's what an engine is, right? Converts heat into shaft power. All engines do that. Or you can run the engine in reverse, drive the shaft, then it turns into a... No? Everybody uses them.
Starts with?
P turns into a pump, right? So any engine can be used as a pump, and any pump can be used as an engine. And the same thing with Tesla's device, right? It can be used as an engine, or it can be used as a pump. So it's a turbine engine, which means it has a shaft, and it has active area, the impeller, and it turns. That's all there is to it. Tesla said it's simplicity itself. It's the most simple engine ever. You put a casing around this, and what happens is the fuel comes in at the periphery. You have a high-pressure jet, just like you have on your oil-burning furnace, burning completely clean. That comes in and doesn't hit a blade. In a bladed turbine, there's a series of blades all around here. Then you have cups, essentially, and these cups then operate by impulse and reaction. This turbine doesn't operate by impulse and reaction. Impulse and reaction is what? It's a banging, right? You impulse, and then you get a reaction from the impulse. Okay? That's tremendously wasteful. It's more of this piston type bang bang type of thing. We want to get away from that. To get a good transition of energy, you have to go from one state to the other as slowly and as smoothly as possible, because any kind of banging, any kind of interruption, impulse, or reaction is going to decrease efficiency. So if you want to have the most efficient turbine, you want to eliminate impulse and reaction. So that was his really big clue, a turbine that does not operate by impulse and reaction. That has blown so many engineers' minds because they've been indoctrinated ever since they've been in school that this is the only way it works. And they see this and it just goes right over their head, even though it's so simple. Because the hot fluids come in and they spiral around now, and then they come out at the center. So you got the hot gases. You just have a series of plates here. It's just a series of plates with spacing rivets in between. There's washers and rivets that separate the plates so the fluid can get in. Okay? And it spirals around and exhausts out the center. Okay? So what is that essentially?
Turbine?
It's a turbine because turbo is Latin for anything that spins. Okay? So anything that spins is a turbine. But
So what is coming through there?
what's coming out of here is hot gas.
What's the fuel sources?
The fuel source can be anything combustible. Okay? So what I was getting to that point. What do we call that? What do you call that?
Spiral.
Spiral. It's a spiraling action, but more importantly, we call that a centripetal, right? But we're looking at another thing we get real scared at here in Wisconsin. Tornado is a vortex, right? A vortex has the most energy of any kind of physical expression. Okay?
So is it the transfer of angular momentum of the gas into the wheel? Is that what it's called?
It's the transfer of angular momentum into the wheel. You might put it that way, right?
Are you burning the gas before it gets to it?
We're
or
burning the
inside
gas
it?
in a burner can, just like any other turbine. Any other turbine would have a burner can and a compressor section in front of it. Okay.
And if you have a hose reel at home and you turn on the water, it jumps. Same principle. The water is coming in from the center and going out to the outside. Transfer of angular momentum.
Right. If you drive this shaft, if I put a motor on this shaft and drive this shaft, it will turn into a pump. And now it's going to suck in the center. Instead of exhausting out the center, it's going to suck in the center and come out and go off the periphery. Okay? So it can be used either way. And guess who is using this technology? Guess who is the biggest promoter of this technology? Well, not the promoter, but they secretly use it.
Power plants.
It's not the power, well, it's the oil companies. Okay, the oil companies have standardized on this in the 1980s for pumping because it's the only pump that can survive. Okay, they can put it in the, they would put a bladed type pump into an application and it could be destroyed in days, literally days. They put the Tesla because the stuff they pump is really nasty.
Like piston engine they were using, you're saying?
No, they were using bladed pumps,
Okay.
centrifugal bladed pumps, which would be immediately destroyed. But they would just keep, before the Tesla in the 80s, they just kept switching them out. There's that kind of profit in oil that they break a pump, replace it, break a pump, replace it. When they came up with these, started using this technology, the pumps go into service and they never fail. Never. Except the bearings might have a problem after hours and hours, but the turbine itself never fails.
Do they have a price on your head?
I think that they aren't too worried yet, although I've been around a long time. It's hard to make headway against the...
So they're buying them from somebody. How expensive are they?
Well, the thing is, they've got the price on these things sky high because it's the best pump, so why not charge the highest price, right? Even though it's the lowest price device to make. And that's what they do. The oil companies.
So they're making their own pumps.
They're making, no, they buy their pumps.
From who?
And I'm going to show you the pumps in just a minute.
Okay.
Here's Tesla. When you, we're a membership organization, and when you join Teva, you get our basic for our basic membership rate, you get a CD just loaded with things, including a CAD program and drawings in the CAD program that allow you to draw or make your own modifications and make your own turbine in the software. But this is our membership manual, and this comes with basic membership. So if you're here's a pump. They're beautiful pumps. They come in all kinds of configurations. It is the finest pump available for any money. Okay? And this pump here would probably be $20,000, $25,000. Okay?
Who makes that?
A company called DiskFlow. Diskflow.com if you want to look them up. DISCFLO. Diskflow.com. And it's amazing what they've done with these pumps. They tried to claim patent protection. That's one thing that our group did, is we went and we confronted these people, said you cannot patent this. They tried. And they failed. No, it's public domain, so you don't have to worry about it.
What's the scale on that drawing?
It's about yay big. I've seen it. And the nice thing about this is you can put your finger right here, this huge pump. You can put your finger right there. I've done it with my little finger, and you pick the pump up. It's made out of composite. For explosion, if it's an explosive pump for the oil industry, they have so many toxic, noxious, explosive gases that this pump can pump that they don't want any kind of metal in the pump. So there's various types. This is non-metallic, and it's really deceptive because it looks like a big, heavy monster, and you can pick it up with your little finger. Okay, and this is the kind of thing that's possible in a car too. Is a compressor that you can pick up with your little finger. So, but the really exciting thing about this, the real exciting thing about the car is that all the R&D has been done. You know, as far as Tesla is concerned, I went to the dinner last night with J.B. Strobel to try to get some information across to him if I could. And I was able to talk to him for a few minutes before I was shuffled away. But I did glean from him that they have no clue. They have no idea about the Tesla mechanics. They don't have any idea about the engine. And even though they're using half of the system, they are in the dark about the rest of it, which is exciting.
Yes.
That is exciting news because you know what he said to me? He said, we'll have to complete the system then, won't we? Okay? So I'm excited. And I gave him my number as a call me. But it's all been done by Volvo. Okay? Volvo spent the money to come up with the concept car, and this thing is the what is it? The model? Oh, it's the Volvo 850. Are you familiar with the Volvo 850? Volvo took their standard production line car, the 850, and they converted it into a Tesla hybrid. long before Tesla. They were trying to meet the state of California's 2% mandate for zero-emission vehicles. California had passed a law that 2% of their fleet, if you wanted to sell in California, had to be zero-emissions cars. So Volvo was forced to do R&D to try to meet that mandate. The mandate was later dropped, and so was the concept that they were working on. But Tesla doesn't have to make all the same mistakes that Volvo did, and Volvo made a lot of them. But there's the car, highest efficiency in its class. They went from 22 miles per gallon on this car to 45 miles per gallon. Okay? And that has a Tesla type engine in it. Now, it doesn't have a bladeless turbine. They incorporate, okay, here's the power plant. In the Volvo ECC. ECC stands for Environmental Concept Car. Okay, Tesla motors are using the Tesla polyphase induction motor on the wheels. And that's a whole other discussion. This is what made Tesla famous. Okay, was his polyphase alternator. Everything runs on Tesla alternators. This is out of a car, 3-phase alternator. Okay, everything. The wind power, everything mechanical that's converting energy is standardized on the AC Tesla system. This runs our world. Runs the ceiling fans in your house. It runs everything. Okay? And that's how Tesla initially got his fame. And that's what Tesla Motors locked onto. This aspect of the technology. Okay? But they did not don't understand that this is only half of it. You got to use the other half. Okay? So they're using the Tesla polyphase induction motor on the wheels. They've got them on the rear wheels and the center axle, and now they've come up with a new version where it's got 2 motors, one on the back axle, one on the front axle. So now you got 4-wheel drive, and those things accelerate twice as fast. It's like, holy cow! But it's controlled. How do they control an induction motor? How do you control a Tesla motor? What's it required to make it go faster and slower?
Change the frequency?
You got to change the frequency. How do you change the frequency?
Rheostat.
Rheostat connected to what? It's called a drive. It's an electronic switching device that switches the current and changes DC into AC. Okay? So it's a Tesla logic. Tesla was the first to patent logic gates. Okay? So anything that has logic gates in it, it's the basis of all computing. That was Tesla's invention, is electronic logic gates. So this is a Tesla logic. They're all Tesla logic. Electronic variable frequency drive. And this changes the frequency, so when you push on the gas pedal, what happens to the frequency? The frequency goes up, applied to the motor, and the car goes faster. Okay? And then you have batteries, of course. What kind of batteries? This was their revolution, right? They started using what? Lithium-ion type batteries, which are a heck of a lot better than the old technology. And this batteries is what has made the Tesla car possible. Advances in this sector. Volvo with their ECC, they were using nickel cadmiums. Lithium ions are much better. But Volvo doubled the weight of the car doing that, putting those batteries in, they doubled the weight of the car, but they also, at the same time, amazingly, doubled the gas mileage.
So what's the function like that for efficiency in the conversion of the DC to AC as a function of the frequency?
Well, you have, like what we're talking about, inefficiencies.
Right.
There's inefficiencies in the controller. When you go from you turn DC in the AC, you're going to have a 15% loss.
But does that depend on the frequency or is it fixed?
It's fixed. Then you have other inefficiencies. The motors are not 100% efficient. They're like 85% efficient. So you have losses there, you have losses here. But those losses don't just add, right? What do? They multiply at a square, right? So it's not just the 1 and 1 makes 2. 1 and 1 makes 4. Okay. But the electronic, so Tesla has given us this portion right here. Okay, and it works. They've proven it works. There's a lot of doubters that said it wouldn't work, it couldn't work, it's going to be a failure. And even JB up on his talk, he said, when we began, we thought we had a 20-to-1 possibility of making it. They fully understood what they were up against. But they've done it. It's amazing. It's mind-blowing. But this is the next step. Okay, Volvo put a Tesla high-frequency alternator. Okay, and a Tesla high-frequency alternator, what does that mean? It's the same alternator, it just goes fast, goes really fast, right? And so if this generator, AC generator, alternator, is going really fast, what happens to the frequency? It goes up. Frequency goes up. So you have a low frequency, and then you have a higher frequency, right? You can put a higher frequency in. What's the advantage of using a high frequency? What happens to the power density as the frequency goes up? Power density goes up. So what happens to the size and weight of the alternator? It goes really down size. So they were using a super miniaturized little alternator, okay, because it was high frequency. Turbine operating at 30,000 RPM. So it's turning the alternators direct connected. And there's a key right there, right? Direct connected so that we don't have any inefficiency losses. So the turbine, they were using a bladed gas turbine, and this was their downfall. This is why the project couldn't work, because of that word bladed. Okay? A bladed turbine, they work. You know, they're in aircraft, they're everywhere, right? But those things are expensive, they require maintenance, and they can explode. You don't want that in your car. Okay? So bladed turbines in vehicles ain't never going to work. Okay? And that's what I didn't realize that Tesla didn't know any of this background. But if they'd done research and found out that Volvo had been involved and failed, they probably would have scrapped it right there. Right? They don't. But if you put the Tesla bladeless gas turbine in here, now you've got something that's safe. This turbine cannot explode. Okay, it's the only turbine to self-regulate its speed. So if it loses a conventional turbine, if you lose your load, say that on the shaft of your turbine, and you're still applying fuel, what will happen? It'll just race right up in speed, and boom, it destroys itself. And pieces flying away for miles. Okay, but this turbine, it has a safety, an inherent physical safety feature, is that it's at the same time it's being used as a turbine. The hot gases are spiraling around. As it turns, there's equal and opposite forces in the other direction, trying to keep it from coming in. Right? So if you lose your fuel supply and this thing starts to race up higher and higher in speed, it pushes and pushes back harder and harder and harder against that motive and self-regulates its speed. It doesn't fly apart.
There's a pushback in that situation.
It's a counter like a counter voltage in a DC motor. Because a DC motor will self-regulate speed. You give a DC motor 50 volts, it turns at 50 volt speed. You give it 100 volts, and it turns twice as fast at 100 volt speed. And it self-regulates. You don't have to sit there and watch it. You just give it the voltage and it runs. Turbine's the same way. Tesla turbine. So you give it the appropriate pressure, and it will not kill you. Okay? So the other advantage of the bladeless turbine, if substituted here, besides cost, Volvo spent, this was their Achilles heel. They spent almost nothing on the vehicle because that was a production line vehicle. But the turbine cost them millions and millions of dollars in development. Not practical. If you use a Tesla in place of it here, now we can use other things like water. Be interested in using water as a fuel? Well, it's a known physical fact that any turbine can use 50% water for its power. It's not a secret. They use it at the peaking plants. Toshiba makes them. When there's too much power and we need to go more power on the grid, how do we do that? If the grid runs out of juice, what do they do? Too many air conditioners on. They start up what they call peaking plants, all right? They're turbine operated. Toshiba makes them. They're huge turbines, okay? But they're bladed types, but they run on half water. How can they do that? Toshiba's running their peaking plants on half water. There's a problem with running water into a bladed turbine. What does that water appear to be? If that water contains minerals, which most water does, right? What are those minerals going to do to the blades when they have an impulse and a reaction? They're going to destroy the blades in short order, right? So you can't just use regular water in a turbine. If you go past these Toshiba peaking plants, you'll see a huge facility, which is the turbine building. Then you'll see another facility right next to it. And what do you think's in there?
Water filters.
Reverse osmosis tubes. They have to have completely clean water, okay? So this brings their water costs, they're almost as high as the fuel. But the thing is, they do it, the reason they do it is because when you water inject into a turbine, what happens to the efficiency? It doubles. Efficiency doubles. So if you're using water injection, you can double your efficiency using water as half of your effective fuel. Because what the water does is it goes in, it combines with the hot gas, flashes into high pressure, high temperature steam, and drives the turbine. But you cannot use tap water or creek water or whatever. You'll destroy it. Okay? With the Tesla turbine, you don't want to have reverse osmosis tubes on board on your car, but you don't need them because you can use water for half the fuel that's contaminated, which means it can contain sand. It can contain impurities to the highest degree. Because remember what we said about the pump? The pump will pump anything, right? So it's the same thing with the turbine. It can ingest solids. You can put the dirtiest, crappiest water in there, and it will work as a fuel. Okay? No expense. That's a complete revolution from the bladed device.
So what is the other fuel?
You can, other fuel?
The other thing
You said add water.
Half water, and that would be a petrochemical like propane or natural gas or gasoline,
Could you use ethanol?
ethanol, kerosene, anything that will burn. It'll even burn biomass. Okay? It'll even burn human waste.
Oh, shit.
No shit.
No shit. So really all you have to do is make up your own fuel, right? You store up your stuff and make some black water, and that's what you inject with the water injection is free fuel.
It because of the rate it's burning, you don't have to worry about any deposits?
No, like I said, it's a complete, it's burning everything. There's nothing left of it except carbon dioxide.
But, but what about the minerals that are in the water? It's not going to burn that.
Oh, it's not going to burn the
But
minerals.
does that deposit even on could that deposit on the inside of the spiral?
Well, they've done experiments with that, and it doesn't. It doesn't. It goes right out the exhaust. Now, because this turbine operates by adhesion and viscosity. Okay, what's it? Adhesion is what? Adhesion is when something sticks to something, right? So if I put a drop of water on this disc, what's going to happen to that water? I think I've got some water here.
Some water on the grass.
We'll experiment. We'll see what happens. What's happening with that water?
Some sticks.
If it would be in a fine spray, it would all stick, right?
Yeah.
But that's what you call adhesion. The little water droplets are sticking right to the disc. What's doing that?
Surface tension.
Surface tension, but that's an electrical effect, right? It's actually being electrically attracted to the disc. And you notice that the drops don't just fall apart, they stick to themselves as well. That's called adhesion, or viscosity. It's viscosity, right? So we have adhesion, the drop sticking to the disc, and then we have viscosity, the drop sticking to itself. And those are the two forces that operate this turbine, not impulse and reaction. Okay? This is a disc out of a pump, out of a blower. So it's a really efficient blower as well.
So the engine has to be made out of stainless steel.
The discs are made out of, this is stainless steel. But you don't, the thing about it is you don't need a high grade of stainless. Because whatever comes in, because the water is cooling the jet. So you never get to the point where you have damaging temperatures to the metal. That's controlled by the water injection. So you never get to a high enough temperature where you're going to melt the thing. You could, but you can use the cheapest grade of stainless. So that is the answer. I mean, I have an idea for the name. It should be called the Tesla Complete. So they have all their standard cars, the S model, but if you had the one with the Tesla Complete, you'd have the S model Complete. Which one would you rather have? The Complete model. The only thing is you might lose one of those dual trunks, which is kind of nice. You'd end up with an engine compartment. But for all the environmental benefits, all the independent benefits, this is something that Amory Lovins had initially promoted here at the fair decades ago. Does anybody remember when he was here as keynote speaker?
No, I remember.
You were Amory's talk? What was his big thing? He's from,
The opposition to efficiency.
he was from the Rocky Mountain Institute, which is a big think tank for efficiency. But their project was the hypercar project. Anybody ever heard of the hypercar? This is the only technology that will practically turn the Tesla vehicle into a hypercar. Right now, the Tesla vehicle is not classified as a hypercar. Amory's vision for a hypercar is a hybrid. And the hybrid, his concept was fuel cells. But there's all kinds of problems with fuel cells, the expense. You have to provide them with hydrogen. It's just not practical. I tried to convince him, drop the fuel cell and go to the Tesla engine. But Tesla has picked up the gauntlet because Amory Lovins was going to start developing these hypercars, but the whole thing kind of got dropped, and then Tesla came along. But Tesla is not at the level of hyper yet. Once you achieve, it's close, but they need to put an engine in it. They need to burn clean fuels and get 300 miles per gallon. Okay, that's a hypercar. That was his concept of a hypercar. A car getting upwards of 300 miles per gallon. Okay, well, we know the Volvo. What did Volvo do with their mileage?
Double.
They doubled it from the 20s up into the 40s, right?
Even though they doubled the weight.
Even though they doubled the weight, right? Well, if we put a Tesla turbine in there, switch out their bladed turbine and put the Tesla technology in, what's going to happen to the mileage? It's going to go up because now instead of just running a standard bladed gas turbine, we can do what?
Water.
We can do water, right? What's the water going to do for us? It's going to double the efficiency. It's going to double the mileage. Right, so we're looking at, with this technology, upwards, just basic technology, which could be improved, we're looking at 100 plus miles per gallon. Okay, and then you put other factors in like tires, aerodynamics, and like we said, that inefficiencies multiply. Well, you can also get that on the good side, because when you have inefficiencies, like inefficiencies in your tires and inefficiency in your airflow, those gains also multiply. Okay, that was Amory's whole point, talking about the hypercar, is that efficiencies multiply against you, but they also multiply for you. Because if we could just double the efficiency again, what would we be at? We'd be at 200 miles per gallon, right? But we know that inefficiencies operate at a square, so it's easier to pick up these improvements to the same factors. And I haven't seen any hypercars, but Tesla is getting close.
Would there be any advantage to just driving the wheels directly from the turbine instead of going through an electrical?
Good question. It's what you call a parallel system. He says, could you drive the wheels instead of doing a series system, which is this? It's series because we're going from fuel to electricity, DC, and then we're converting back, and everything is in series with that motor. It's a series system. Whereas a parallel system, you would extend the shaft out and drive the induction motor directly, or a direct drive. In other words, it would be a mechanical connection, right? So you could go either way. On a parallel system, you can operate electrically and make the motors do the work, or you can drive it with a shaft directly and have a pure mechanical connection. Is there an advantage to doing it that way? No. Although Tesla did come up with the same technology, can be used in transmissions. Okay? It's a bladeless torque converter. Tesla was actually, we've got pictures, I have to dig them up, but I've got pictures of automobiles, motors, V8s, using the Tesla device as a load. So it's a dynamometer. They've actually built dynamometers out of these things. But no, there's not an advantage.
Is there any company or person building the small Tesla engines?
Question, is there anyone actually building these companies that are into building these? The only commercial application that you can get right now for a Tesla device is the pump. But I would suggest if you want to get into experimenting with these and playing with these, that you start with the pump. Because the pumps are very expensive. You can't really afford to go and buy a pump, but you can build your own for almost nothing. Okay, what you can do is you can go out and get the discs made. You can have the discs laser cut. What you do is you go in the CAD program and you design the disc, and then you send the file out to the laser cutter, and they return you a bunch of discs. And it's that simple. Okay, and then once you have the discs, you can assemble them, put the spacers in or tie it to the shaft, however you're going to do it, and make your own. Take a standard pump, take a standard centrifugal pump with blades in it. You take the blades out and you put the discs in, and that's an easy conversion. All you have to do is get the disc laser cut, assemble the runner, and put that in the old pump housing, and you've got a Tesla pump. And it is such a beautiful pump. I mean, it's the gentlest pump ever made. Got pictures of pumping applications. Okay. There's a pump runner. So all you would do is you construct this, and then you take the standard pump, take the blades out, and put the bladeless in.
So, what? In order to use it as an engine instead of a pump, you'd need to use stainless steel, basically.
Right. If you're going to use it as an engine, you need stainless.
Okay. Is there a way to laser cut stainless?
Yes. Same process.
Okay.
All this was a file. This is all done on CAD. And if you join Teva, you get the CAD program. You actually get the CAD program, 3D modeling program that you can actually make your own discs. Okay. Any other questions?
So are there working models of that turbine, brand new bladeless turbine?
Well, there's all kinds of working models. I'll show you one.
Why don't you have one to demonstrate?
Because it was such a. I do have one. I have a 21 inch. I have one that's this size, but the thing is a monster to get in here. I could have brought it. I was thinking about it, and then I thought, no. Okay, here we go. Here. When we came out with our plans in 1994, we came out with plans and said, okay, we've got the plans now. We went back to the original Tesla assembly drawings, which no one had done before, and we got the actual original Tesla plans to build the turbine. And then we published them, okay? And then we had people actually take up our challenge and start building the engine. So this was the first turbine that was built off of our plans. It was the first properly built Tesla turbine since Tesla himself. So this was back in '94, and this was the first attempt, and it's a really sweet turbine. This turbine has proven itself over and over again. The Department of Energy tested it. I was at Telluride, Colorado. I gave a talk at the Telluride Tech Fest, and there was someone in the audience from a research engineer who was trying to get turbines to burn biomass. Okay, they were trying to employ bladed turbines to burn biomass, but what's the problem with that? The particulates destroys the turbines. They found that out in short order. So when they heard my talk, they said, well, there's a technology out there that might work. So they invested money, and they got the California Energy Commission to put up a grant to test it. Okay, it's a $60,000 grant. So they took that money and they took our turbine and put it onto a biomass burner. And this is all documented in our literature. If you want to find out more about this, everything we've done is documented. All the different turbines, it's all been documented. So if you were wondering, well, could this be real? We made sure everything document one step at a time. We've been at this for a long time now. But this turbine burned biomass. They put it on their biomass burner and they burned coal, corn, soybeans. That's what it was. Corn and soybeans through the turbine. And they were afraid to run more than 10% solids through it. Because the bladed turbines that they've been experiencing, if you put more than 10% biomass into the turbine, it would immediately be destroyed. So they were worried. Said, we're going to destroy your turbine. I hope you understand that you're going to have a piece of garbage when we're done. And I said, well, if you can wreck it, go ahead and wreck it.
I don't understand where this pressure comes from that's going through this turbine when you're burning that fuel.
The pressure comes from pressure like any other gas turbine, from a compressor and a burner. On a conventional turbine, you have a burner section, or you have a compressor, and that feeds air into a burner, and then that feeds into the turbine. So, it's just like a conventional setup. Just like Volvo did it.
Is that nozzle down there, that variable nozzle? Is that where the pressure goes?
This is where the pressure comes in. And this is kind of interesting because this variable nozzle right here, this was in Tesla's, Tesla designed it and patented it and drew it out, but he never built it himself. This is the first time that this patent from Tesla was actually employed. And you know, this was built in a garage. This wasn't built at any kind of high-tech, well-funded facility. This was built by an amateur in a garage.
Can you explain why the combustion is more complete? Are the products of combustion reburned because of the heat, or what is it burning?
It's because of dwell time. There has to be enough time for the combustion products to actually completely combust. With a piston, you don't have that kind of time. It's instantaneous, and then the opportunity for combustion is gone. So you end up with all these waste products. If you have enough time and enough temperature, that's the other key. You have to have enough time and temperature to completely convert that fuel.
Could you address the opposition to Tesla? Because there's...
Well, that's an interesting point. I talked about the biomass testers where they're putting soybeans and corn in there. Well, this young engineer, he got the grant from the California Energy Commission because they didn't know what he was doing. They didn't know he was going to test the Tesla turbine, or they would have said, forget it. Okay? Because that's how verboten it is to... But he didn't understand. He was altruistic young engineer, and he was excited when this worked. He said, this is the answer. This is it. This is it. You know, he was super excited. He was going to dedicate his career to this technology. Okay? I said, oh, great, finally. I called back on the phone several months later, and he says, I said, well, what's going on with you now? He says, I have a family to feed. Click. So that's where it is, that political opposition. Even though it's the best technology that they've ever seen, they can't, there's no money.
No money.
No money.
So out of the combustion chamber, what's the pressure coming out of there, and how does it get to the to there? In other words,
At the pressure you want at the nozzle is between 80 and 185 psi. Okay? The higher the pressure you go at the nozzle, the higher the speed is going to be, and the higher the efficiency is going to be. So, yeah, that's critical. You have to have, it's what's called a velocity machine. It doesn't work by volume. It works by velocity, primarily by velocity. Because does anybody know what power is equal to? It's not just the mass, it's the velocity. But guess what symbol is over the V in that equation?
Square.
Square. Okay, so there you have an exponential effect. So if you don't have velocity, you're going to drop off power very rapidly. It's a velocity machine.
So what controls? How do you control the pressure out of the combustion chamber so that it's at the right psi?
Well, in the automobile, this would just run at one fixed speed. It would run at its highest efficiency speed, like 30,000 RPM, and would just stay there. So you would just adjust the fuel, and then when you get a load on the car, it would up the fuel. Because this is going to hold you back. It's also a pump and a turbine. So when you're acting as a pump, fluid's coming in, but it also has back pressure coming out. So if you want to go faster, you got to increase the pressure. Okay, other questions?
Where's the exhaust on that turbine? On the one on the. Is there
Oh,
any
it's
sort-
on the other side.
It's not out the middle, or it's out the middle.
But I would suggest that what you can do is go over to our website, and you can get for a free download. You can get the current issue of our newsletter.
How fast would that turbine be spinning with a gas engine, car engine?
That one depends on the diameter. As the diameter goes down, the speed goes up. As the diameter goes up, speed goes down. Because it's peripheral velocity is what you're concerned about. So as the size goes down, you have to increase the speed to maintain the same peripheral velocity. As the diameter goes up, you're going to have higher peripheral velocity, and the speed RPM goes down.
You're talking hundreds of thousands or what?
This would turn at about 7,000 RPM in a car. If you had something this large, but typically what they do is they reduce the size so it's got a small footprint, and then they run them at higher speeds, like this would run about 30,000 RPM.
How many blades are there?
The number of discs can be variable. Depends upon how big of a load you want to have on your device. You could have many. If you wanted megawatts, you could have many discs. But something small like this, Tesla claimed that 26 discs at 9 3/4 inch could easily produce 1,000 horsepower. So you got 1,000 horsepower. It's something that you can hold in your hand.
Well, what do they use for bearings?
That bushings is typically what's used, but they've been experimenting with magnetic bearings, which is the ultimate. Like an air. Yeah. Right. Bushing type of situations. That's what Tesla used.
It also, some biographers of Tesla think that was his holding point was the bearings. He couldn't, he hadn't came up with a bearing that would actually handle this high speed.
Right.
Because at that time, you only had.
Bearings are problematic because you are turning at high speeds, but it's a well-established technology now.
But not magnetic bearings.
Magnetic bearings have no problem. They float in a magnetic field. We're just about out of time. I mean, please go to our website, teslaengine.org. teslaengine.org. Because I just don't have enough time to even begin to give you all the details. But like I say, everything has been documented. We have the current newsletter is available to you online. Here is a little turbine that Tesla built. Here's the turbine. Here's the high-speed alternator. This is what would be in the Tesla. This is what you would have under your hood.
Is that product available?
No, this was built by Tesla. And this is a rare, we just got this photograph released from the museum in Belgrade. This is a very rare photograph. We have other photographs that you can get from us that have this entire thing torn apart. So we have the photographs of this, all disassembled. Okay, so if you're interested in building this, and it's built totally buildable, simple. But we have all the pictures of it taken apart so you can look and see exactly how it's put together. Okay? But I'd encourage you to go and get a copy of this newsletter.
Right now.
Membership,